Hello everyone and welcome to Cloud Native Wednesdays. My name is Alexia and I am one of the project managers at Microsoft Reactor. Today we're going to finish season 2 of Cloud Native tracks in the Championing Azure Collection series. Before we begin, I would like to go over a few items. Our code of conduct. Our code of conduct here. Please take a moment to review what's being shown on the screen. We all come from different backgrounds, so let's be aware of each other, be friendly and patient. After all, we're all here to learn. Thank you so much. Which brings us to today's session. Let me introduce you to our speaker, Alan Smith. For most of you, I believe Alan is a familiar face by now, but for those who don't know him too well, Alan is an Azure MVP based in Stockholm, Sweden. He's a developer, mentor, trainee, teacher, and local Azure and AI community leader who has been awarded as the MVP of the year, as well as been once recognized as one of the top 10 developers in Sweden. The session will run for approximately 45 minutes and some time for Q&A at the end, but I do encourage you to ask your question as the session goes as well. Feel free to just drop them in the chat. I'm going to bring in our speaker in now. Hi, Alan. How's it going? Oh, I think you're muted. Can you try this one more time? Apologies, everyone. Just bear with us 1 second. I think you're still muted. We can see your screen though. Alan, I'm just going to add you in the screen if that's okay. The joys of live streaming. Apologies, everyone. We will be right there.
Hear me? Please type something in the YouTube chat, and then at least I know I'm getting out there somewhere.
We can hear you here. Yes.
Yeah. I should be fine as long as it's coming through on YouTube. Then it should be hopefully okay.
Yeah, absolutely. It is.
Yeah. Okay. Sorry about that quick delay. So what I'll do is I'll share my screen, share the other screen. Sounds like the police are coming.
Yeah, I think it's on my side. I'm just going to mute myself for a quick sec.
Yeah. Okay. Hopefully we've got the screen there now as well. Good. Yeah. So what I'm going to do in this session is basically run through a presentation that I've done a number of times, looking at using Cosmos DB and looking at a scenario with data that I've taken from the Game of Thrones TV series. So a bit about myself. My name's Alan Smith. I describe myself as a developer, trainer, mentor, and evangelist. I work for a company called Active Solution based in Stockholm, and we build solutions for customers. Most of our customers are running on Microsoft Azure. So we've got quite a long history of working with Azure projects. adopted Microsoft Azure very early on when it was first released in preview mode, when not many people were actually building systems on it, and we invested a lot of energy in learning how these technologies work, and it's paid off because in the past few years we've seen a huge move to Microsoft Azure, and Cosmos DB is one of the services that we've used in many of our projects, so it's very relevant to the real world projects that we are working on. I do a lot of work with the community. I put quite a few videos out on YouTube, and I think I've got this video as a demo out on YouTube, and then also one on the auto-scaling capabilities in Cosmos DB. So Cosmos DB, when I first heard the word, it kind of reminded me of the TV series. I remember watching this when I was about 9 or 10 years old with Carl Sagan, and I think they've done another more modern series of that. So I pronounce it Cosmos DB, as in that TV series. I've heard it pronounced Cosmos DB, which kind of reminds me or Cosmos DB, which kind of reminds me as Cosmo Kramer from Seinfeld, which doesn't kind of conjure up the same image of, something that's huge galaxies and has lots of capabilities. So Cosmos DB provides a number of capabilities. So this is kind of the selling pitch for Cosmos DB. It provides global distribution, meaning that I can have my main data stored in West Europe, and then I can decide to distribute replications of that data to the US, out to Asia, down to Australia, different regions in Europe, down to South America. So I can basically choose to have my data distributed all over the world. That gives me good reliability. And it also provides low latency for people accessing data in other regions. We've got elastic scale out, so the capacity of Cosmos DB can change dynamically based on the load that we are placing on that database. We have this auto scaling capability within Cosmos DB, so it will react and modify based on the amount of load that we're placing on that database. Cosmos DB, unlike some of the other data services, provides a guarantee of low latency. So I think the guarantee is something like it is 10 milliseconds read and 10 milliseconds write for 99% of read and write operations, which is pretty good for low latency, but also to have that guarantee on performance is really great if you're building mission critical and business critical systems. We have a number of different consistency models. This is related to something called the Payselp theorem, which talks about having to have a compromise between latency and consistency when we have a globally distributed system. So we can choose to prioritize consistency, or we can choose to prioritize low latency. And we've got kind of 5 different levels that we can set when we're making that trade-off between having low latency and having a highly consistent data model. The service level agreements are very comprehensive and do include the guarantee of low latency. So this slide basically shows how we can connect applications to Cosmos DB, what APIs we have available. We can use a table storage API, we can use JavaScript, we can use a SQL query language to be able to query Documents DB. It also provides compatibility with Mongo database, which is another sort of very popular non-relational system. We've also got Cassandra, which has also been added fairly recently. And what I'm going to be focusing on in this section is looking at the graph model in the database and looking at the Gremlin API. We've actually got 4 different data models. We've got key value, column family, document, and graph. And document is probably the most widely used one. This is used for storing hierarchical JSON documents. So within the Azure subscription, I've created a Cosmos DB account, and if you create it with the Document DB, then you generate databases, and within the databases, you generate collections of documents. However, if you've chose to use the Gremlin, the Graph API, then you create databases, and within those databases, you create graphs instead of collections. And they're going to be used to store the information and the relations between those informations. So running through the different data models, key value is very straightforward. It's kind of like a configuration where you've got a key and you've got a value, but it provides a very high performance, globally distributed configuration store. We've also got the column family, which is very similar to Azure table storage, where we can store basically using tables and storing entities. We can store entities within tables and have very good capabilities on querying those. The tables do not have a fixed schema. So you can see that some of the entities have different properties than other entities, but that doesn't matter. We're not defining a table schema. We're just able to store these entities and properties within that storage system. Document, we can store hierarchical documents, and they're very often stored as JSON documents. I have a webcast on my YouTube channel where I'm storing tweets, which are quite complex, hierarchical JSON documents, and storing those in the Cosmos DB document model, and then running queries on that to select the tweets where, from users with over 10,000 followers and things like that. So what's this Gremlin creature doing? Well, first thing about Gremlin, you can tell that it is not a Microsoft technology. When you look at the Microsoft icons for their technologies, it tends to be some kind of representation of what the technology is. So we've got things like Cosmos DB, we've got Logic Apps, we've got Azure Functions, and we've got various SQL technologies. However, the open source community have this thing about picking animals for their actual icons and logos and so on. And the Cosmos DB icon is basically one of the Gremlin icon is one of those. It's a graphing technology that's used as a query language for being able to query graph databases. So on to the idea that I got for working with the Game of Thrones data. When I was learning about graph databases, I came across this article on this Neo4j blog. So Neo4j is another graphing technology. It is different from Gremlin. There's not much compatibility between Neo4j and Gremlin. And there was this competition running in the Neo4j community to be able to take the data from the Game of Thrones TV series and then be able to visualize that data using the Neo4j data engine. And these are a few of the actual submissions, looking at these various characters and looking at how the characters are connected together. We'll see in a bit more detail how we can build these models within the graph database. So here we've got a number of characters. This is shown as another graphical representation. And then we've got the relations between the characters. And a graph database is really focusing on these various relations. You can see we've got married, we've got people who are allies with, people who serve, people who have killed another character. You can see there's quite a lot of those green arrows present there. And then we've got various other options like that to be able to show how these entities are connected. Here's another more complex one, showing various characters and how those characters are grouped together. And they've also done some clustering to show these in different colors because they belong to different families or different houses and so on. So it gives you an idea of how people are connected within Game of Thrones. So real world applications for this technology. If you have something like a LinkedIn account, you've got a LinkedIn profile. When you connect to LinkedIn, you say, well, I'm working for this particular company. I went to this university. I studied at this school. I'm living in this particular city. And then you start to, build up contacts in your LinkedIn list. And it will come up with suggested contacts. These are people who you may want to connect with. And so within LinkedIn, they probably have a graph database, which looks something like this, but a whole lot more complex, where they're showing all of the actual LinkedIn profiles and how those LinkedIn profiles are connected to each other and connected to companies and connected to various, schools and universities. And from that, they're able to, come up with these friend recommendations, who has the most connections with somebody else, but is not connected to another person. You could see Robert and Caitlin. I don't know if there's an actual direct connection there, but there's certainly a lot of other characters that do share connections between these two. So you could probably suggest that as being a good friend or contact recommendation. This is another one of those. It was AI predicting who would die next in Game of Thrones. I think this was before the last series, and that was the prediction that it came up with. I'm not going to go through any spoilers in case you haven't seen the series. So TV series, I did briefly consider The Walking Dead, but it would kind of look like that, and there wouldn't really be too much complexity in that model. The Game of Thrones does provide a really rich model for exploring using a graph. So the data I got for this was from the Game of Thrones wiki, and you can see basically looking at one of those character descriptions, we've got loads of information about how that character is connected to various other entities within Game of Thrones. Some of these entities are other characters. So we've got the father, we've got the mother, we've got the various siblings, and if they've had children, we've got the children. We've also got connections to whereabouts they were raised, the allegiances that they have, House Stark, House Targaryen, and Night's Watch. And then we've got the culture that they come from. We've got the religion that they worship. And so those can all basically form entities or nodes within the actual graph database. So kind of think of it like within LinkedIn, it's going to be like the companies you have worked for, the the school that you went for, the city that you're living in, the city that you grew up in, and all of these various entities that you can share connections to with other characters. So looking at database models, you've maybe heard of relational databases and non-relational databases, and graph databases basically share with these two different data models. In relational databases, we really focus on the data, but there are relations between those actual data entities. In non-relational, we don't have any relations or connections, but in a graph model, we're really just focusing the database engine is built to be able to handle all of these different connections that we've got between the entities. So if you've worked with SQL Database, you've probably written horrible queries like this, where we're basically joining and getting information out of a database. So here I'm pulling out data from an order from the AdventureWorks sample database, and every time you do a join query, it increases in complexity in the actual system. And you can see what that query looks like when we run it in the query analyzer. It's pretty horrible. So we generally, if we want scalability, need to move away from relational databases and maybe go into something slightly different. So if I was going to build a Game of Thrones in a relational database, I generate my persons table, I generate my table for the houses, and I'm going to model these allegiances. So that's Tyrion Lannister, who basically serves House Lannister. And then sorry, that's really creepy. I didn't realize that will be animated when I copy pasted that. But Varys also serves House Lannister. So you kind of build this, entity relationship table, and you build these foreign keys to link these two tables together. However, what happens if Varys serves Tyrion Lannister? Our database model doesn't support that, because people basically serve houses. And we need to modify the database model to say that, well, people can also serve people as well as houses. Maybe if you're a priest, you could serve a religion and have an allegiance to a religion. So the graph model basically doesn't have those restrictions. We generate a vertex, which is House Lannister. We generate a vertex for Tyrion, another vertex for Varys, and then we can generate the edges. And we can basically put these between all of the different vertices. It doesn't matter whether the vertex is a house or a person or a religion or a culture. We can just basically create those relationships, and we can also define what the relationships are. It could be father, mother, married to, serves, worships, whatever. We can basically define the names for those particular database edges. So bringing in Gremlin, this is a language for doing traversals across graphs. I keep saying that we query the graphs. We don't actually query the graphs, we do a graph traversal. And what that means is we basically send in some kind of a question, and we get results back on the actual traversal that we are going into. And there's various steps in those. I'm not going to get into too much complexity about how the language works. I will show you some demos of how this works. But it is really NoSQL. It is not the SQL programming language. So I could do a query like that in SQL. However, in Gremlin, that query would look like that. What I'm looking for is all of the actual vertices that Tyrion serves. And I just do g.v. This is the vertices with the name of Tyrion, and then all of the outbound relationships with serves, and everybody who's connected with an outbound relationship of serves. So it's much simpler to do these kind of queries that would be very complex queries with multiple joins if we were to do that using a regular relational database. So I'm going to skip the first demo and go into the next demo, just talk a bit about the data harvesting that I did. So I went to the Game of Thrones wiki site. I did originally go around on a website called Kaggle and basically try to get a pre-prepared data set. And all the data sets I found didn't really have the same level of depth that I would have liked. So I basically started screen scraping and says, well, let's look at this actual page. Let's look at this information here. And from that, we can basically extract and get this out in JSON format by basically reading, all of the tags on the page and formatting it in JSON format. So if we start with go through the list of characters, that's also going to help us to build up the various titles that the character have, the allegiances, the cultures, and we can build up these lists of the cultures and basically all of the characters present in there. And once we've got this JSON, we can start to add the information from the database. So here, g.v, g.addv is adding a vertex. The vertex is of type character, and it has a property, which is the ID property of Jon Snow. And then we can basically add the edges. So g.v, and then we've got is it Rhaegar Targaryen, and then I add an edge saying is father of Jon Snow, and then I can drop on is mother of Jon Snow. And then I can say that Jon Snow serves House Stark, Jon Snow serves House Targaryen, serves the Night Watch, and go through that and add on all of the actual edges, all of the actual connections. So I'm going to run the demo to be able to, this is basically what it will build up for Jon Snow, all of the actual connections that he's got to all of these other entities, all of the actual edges present on them. Okay, so I'm going to jump into Visual Studio, and within Visual Studio, I've actually created a Cosmos DB database, which I am connecting to. So within the portal, I'm in my Cosmos DB account. I've got this account called Graph of Thrones. So if I want to, I can add another second graph to that. I've already got my DB of Thrones, so I could add Graph of Thrones 2. And I specify the partition key, and I'm using key in my examples, which is a property that I've got on my entity. And then we can configure the scaling on Cosmos DB. Here, we're using the auto scale. So these things are called request units. Whenever you run a query on Cosmos DB, it will consume a certain number of request units. And dependent on how complex the query is or how much data it's returning, that will affect the number of request units. So if your queries consume, say, 40 request units, then I can run 100 queries per second at this maximum scale capacity and 10 queries a second at the minimum scale capacity. So if I need more capacity on that, I can add noughts to the amount of capacity, which adds noughts to the amount of monthly cost for this. You can go up to crazy amounts. You can see the actual estimated monthly cost for this is getting quite astronomical for that. So I'm not going to go for anything that crazy. I'm just going to go for the 4,000, which if it's running at very low capacity, it's going to be $35 a month. If it's running continuously at the maximum capacity, about $350 a month. You can, if you have a very steady load, go for a fixed capacity. And here it's going to cost me $23 a month to have those 400 request units. So you've really got to think, have I got a spiky load or have I got a really level load, and choose the amount when you create the database. It is very easy to modify this. So if you do find you've provisioned too much capacity, you can very easily dial down the capacity to reduce the monthly charge. So with those settings, I could click on OK, and I could create that new graph within the database. However, I do have a graph that I've got present, which is this Graph of Thrones one. I can go to the graph there and I can run this query and query the actual data that we've got present. So I ran a very quick trial run just to actually try and get a bit of data into my database. I really want to close these windows a bit so we can actually see the see what's coming back from this. So I have just basically put in a few entities in that. I'm going to jump back to Visual Studio and repopulate this with all of the actual data. So this is graph-of-thrones.json. You can see the actual format of this, and if I scroll down way down to the bottom, it's about 9,500 lines of data. So there is a lot of stuff there. So if I run this, it's going to do g.v.drop, which basically clears out the entire database. That deletes everything from the database. And now I'm adding the characters. And you can see every character is a particular query that's going in. I'm specifying the ID, and I'm specifying the key of that is going to be a character. We do occasionally get an exception. The data isn't as clean as I would like it to be. We're now adding the various allegiances. We're adding the cultures and the religions. And now we're adding the edges, which is how those different characters are connected to one another. And hopefully it's not going to take too long to get this data present. I did configure it with auto scaling, so it will increase the capacity of the database when I put quite a bit of a load on that. But hopefully we will start getting, I think most of the actual edges are present on there. I'm just going to drop that onto my other screen, because here we can go and we can look about actually querying this database. Okay, I'm going to drop back, just run through a few more slides whilst this is running and talk about the data model. So when I've imported it, there's about 823 vertices, 660 characters, 128 allegiances, 29 cultures, and 6 religions. 1,928 edges. Serfs is the most common one, and then we've got his father of, we've got his mother of, we've got his married to, 102 marriages in there. And then also is from the, I think that's the culture that they're from, and they worship a particular religion. So you can see out of those characters, 186 of them are religious. Okay, so that has actually basically imported all of my data. I'm going to go into talking a bit about the actual traversals that we're working with, and I kind of think it's a bit nicer to actually demo this in the actual query window, rather than just to run through the slides of run through the various slides of how these queries work. So within the graph, we've got the option to drop in our own queries, if I can find that. So where was the query? So I need to go here. I need to go to the Data Explorer, and then into the Graph of Thrones graph, and then I've got my Gremlin query, so I can fold up that and fold up that, I think. So what I'm querying for here is g.v, and what that is returning is all of the vertices within the Game of Thrones graph. And what we get displayed here, if I just hide that window there, is basically from that query, we get back all of the actual vertices. So we get Eddard Stark, we get Jaime Lannister, Catelyn Stark, and all of the actual characters like that. Now, what's provided here is a visualization. It's showing Eddard Stark, but it's also showing the entities that Eddard Stark is connected to. Now, this is not part of the query. This is just a visualization that is provided in the portal interface. But it's a really nice way of being able to actually look at this particular graph. So Eddard Stark is collected to House Stark. You can click on House Stark and you can extend House Stark. And it shows you other people who are connected to House Stark. So you've got Jorah Mormont and Peter Baelish. You can go into Peter Baelish and look who he's connected to, and then you can see other connections that we've got from Peter Baelish and so on. So there's a House Baelish here, and you can see who's connected to House Baelish. And if you click on that, we've got other characters popping out there. So that's a nice way of being able to navigate this. You also get the properties. So if we look at House Baelish, if you look on, say, Peter Baelish, you've got these characters that serve House Baelish. However, if I go back to, say, Jaime Lannister, you can see the actual who he is, who is father of. You can see his parents here. You can see basically who he served, and his children as well here. So we can also do more complex things. What I can do is do a g.v.count, and that's going to show us that we've got 872 of these vertices, and then I can look at the label, and then I can do a .group count. And that's showing me, the characters, the allegiances, the cultures, and the religions. So G.V is querying the vertices. If I do G.E to query the edges, then that's showing us all of the different relationships that we've got. Now, to query a specific vertex, what I can do is G.V, and then I can drop in the name of the vertex, which in this case is going to be a character. Put in Eddard Stark and run that query. And ignore the graph bit. This is what we get back when we query for that particular vertex. We get that Eddard Stark is a character, and this is the information that's coming back from that particular vertex. And then we can start to query the actual relationships. So if you want to find out the children of Eddard Stark, then we look at the out relationship, or the out edge, which is going to be is father of. And run that query, and we get everybody who basically we get all of Eddard Stark's children. Anybody where there's an outbound relationship from Eddard Stark to that character, and the relationship is father of. We can find out who Eddard Stark's father is by doing the in relationship is father of. So this is querying for Eddard Stark's father, which is Rickard Stark. So if I take Rickard Stark and drop this in here, and then change this back, we can see who his father is, and that's not listed, so we can go for Rickard Stark's children. And then if you want to query Rickard Stark's grandchildren, you can do that. So this is going down to the children, and then on the children we do out is father of, and that comes out with Rickard Stark's grandchildren. So being able to navigate that the graph language is very useful for being able to do these types of queries. Remember, if I was doing this with a SQL database, and we had all of these foreign keys and relationships, it would be really challenging to be able to build those types of relations. So looking at doing slightly more complex queries, I'm going to copy paste this one. This is basically looking for the most influential institutions. So if I drop this one in here, so what I'm querying is I'm looking at each vertex and the outbound relationship that has serves. Now, I'm not limiting the vertex to being a specific type of vertex, like a character or a house. It's just basically going to be any vertex. And we're looking at the out relationships that serves. And then what I'm doing is a group count on those out relationships, which means we're going to get all of the vertices, look at how many outbound relationships they've got with serves connected to. And then what I'm going to do is an order by clause, and order by the value in a decreasing order. So what that's going to give us, and you can see that it's not displaying the graph anymore, it's just giving us a pure JSON view, because we're just querying back and we're getting numeric data. We're getting back House Stark as being the most influential. So there are 86 entities within the actual Game of Thrones world that do actually serve House Stark. And then you can see House House Targaryen, the Night's Watch, House Lannister, House Baratheon of King's Landing. And scrolling right down to the bottom, you see all these little houses that you've probably never heard of or never remembered if you've watched these, like the Iron Throne, the Alchemist Guilds, King's Landing, House Holland, and various things like that that only have one entity that is actually serving them. So what the kind of main goal on this when I started out doing this project, it was to be able to model a Game of Thrones world and do the same type of thing as was done in those blog posts on the Neo4j. There were so many people that did this with Neo4j, but I didn't see anybody doing it with the Gremlin API. I didn't see anybody else doing it with Cosmos DB as well. So I decided to take that challenge of modeling the Game of Thrones, but do it using a different technology. What I also thought of doing is it would be really fun to build a friend recommendations for the Game of Thrones. You've kind of got that in Facebook and in Twitter and so on. Being able to say, based on the connections that you've got within this world, who should you consider making a connection to? Who would be somebody who you should consider connecting to? So what I'm doing, if I can drop back to the slides, is thinking about the actual friends connections. So here's Jon Snow, and he's connected to, it's so long since I've done these slides, I can't remember what these things mean. I think that is something to do with the religion or something, and that is maybe something to do with a house, and that's probably another house that he has an allegiance to. So he basically serves these three entities. And then you've got other characters within Game of Thrones that will also maybe serve these entities. And what you can do is say, well, there's a connection here between the middle character, because they share the most amount of connections with the same entities there. This one is going to have two connections, so that one's going to be maybe a friend recommendation, but not as high priority as this one here. And then this one down here only shares one connection, so that's going to be lower on the recommendation list of being able to do a friend's recommendation. So you're really looking at who do I have the most in common with, or who does Jon Erin have the most in common with? So to build up that query, what we're doing is looking at the vertex for the character. So I'm querying g.v Jon Erin. The next thing we need to do is to traverse to the related vertices. So you've seen that I've been doing .in and .out for looking at the direction of the relationship. When you're looking at is farther off, you're looking at kind of at the direction of the relationship. Here I'm doing .both, which is going to cover the inbound relationships and the outbound relationships, because you're going to want to have these running both ways. You're going to want to maybe so your children is going to have an outbound relationship and your father is going to have an inbound relationship. So you want to query on both directions for the relationships. And then what you're going to get here, if you do the first .both, is you're going to be getting a bunch of like houses and religions and cultures and various things like that. They're not going to be characters. So if we do a .both again, then we're getting the entities that have connections to those various houses and religions and characters. Sorry, houses and religions and cultures and so on. So a substantial number of those are going to be characters. However, it's not completely guaranteed that it's going to be a character, because if Jon Erin serves a particular person and then that person serves a particular house, then you're going to be getting the actual house being returned in here. So what we want to do is to limit this to the actual characters. It's only going to be characters that we're going to be doing a friend's recommendation on. And then we want to count the number of relationships that we're getting from that particular query. So we're doing a .group count. And then we're doing our ordering, and we're ordering it by that count in descending order to be able to come up with the actual full query. I don't know if there's a better way of doing this. This is basically what I came up with when I was building it. I didn't really read any books on this. I didn't really study the query language. I just basically figured out that that is maybe a nice way to actually look for friend relationships, but there's probably other ways of being able to solve the same problem. So game of friends, I'm going to run that query I've got it in my my notepad, so I can just drop into the here and just run that particular query here. And you can see that it's coming out with House Stark as being the most. Oh, sorry, I got the wrong one. Sorry, that should have been the friends query. I'll try that again. Where was this query here? So this is coming out with querying for the friend relations for Jon Erin. Now, Jon Erin is going to come out on the top, because if you think about it, he will share the most connections with itself. When I'm doing .both, it's basically figuring out it's basically figuring out all of the things that he is connected. So he's coming out in the top. So I should actually probably try and modify this query. I'd probably fail if I tried to do it now, to say that the name is not equal to Jon Erin. I'm not sure how to do a not operation in Gremlin. So what I could say is if they're not Jon Erin, then basically exclude them from that. It will be maybe something like has not name of John Erin or something like that. I should really look up how that works. But it's coming out with Peter Baelish as being the top friend recommendation in the Game of Thrones world. If you've watched Game of Thrones, I think you should be seriously worried if anybody is recommending that Peter Baelish is going to be your top friend recommendation. It probably means that you've got some really bad connections in your social network. However, we can take Peter Baelish and we can drop Peter Baelish in the actual character name, and we can see who Peter Baelish should have as friend recommendations. So he's coming out at the top, and then we've got John Erin with 10 connections, Robin Erin, and these are all kind of connected to people that Peter Baelish has been communicating with and connected to as we go through those as the series has developed. We go through Caitlin Stark and drop in Caitlin Stark and just see who she is getting for the friend recommendations. And you can see that a lot of the friend recommendations are coming back from her own family: Robb Stark, Arya Stark, Sansa Stark, and various options like that, and then connected into other families that she does have connections with. So I did manage to kind of achieve that goal of being able to do friend recommendations in the Game of Thrones. So I've just chosen a really kind of a fun scenario for this. The reason that I did this is I kind of wanted something that would resonate with developers, because when I was teaching classes and presenting on Cosmos DB, I'd basically show these various models that we have. If I can find the actual slide that had these data models, and just bring up that slide. People kind of understood the concepts of key value and column family and documents. They kind of understood what a document DB was. However, when it got onto the graph model, people didn't really understand what it was about, and without having a really nice demo that could resonate with people, it's kind of hard to get across the idea of when you should use a graph database. Also, the complexities of building something on the graph model. I had no idea, how complex it is to use a Gremlin. I've never written a Gremlin traversal before. How is this going to work? Is it going to be easy to do this? How well is it going to perform when I want to query something like the actual friends recommendations graph and get information back on that? But it does seem to perform very well in my particular scenario. I'm just going to drop back and see if I don't know if it gives. Yeah, it gives a query stats. So the request charge here is saying when I ran this query, it's costing me 140 of those request units, and I think I had 400 per second on the minimum tier and 4,000 per second. So I could probably run almost 3 of these queries per second at the 400 tier. However, I try some of the simpler queries. If I just look for something like this, run that query, look at the query stats. That's only costing 10 request units. So it's very easy to be able to estimate, what kind of capacity you're going to need. If you know what queries you're going to be running against the database, you can look at the kind of average request charge. You can think about how many pages per second your application is going to be running at, and that's going to kind of help you to be able to assess the actual capacity of that. I think maybe there's going to be some metrics on this because I did upload the data, and we can maybe see in the metrics section. I don't know if we see in the overview the actual load that I'm placing on the database. Yeah, this is when I did the original upload of the data. It's yeah, that's when I did it. Yeah, 5:56 during this session here, just as the session was starting. That's when I was uploading the data, and then I think in the monitoring we should be able to see a bit more. I don't know if the auto scaling has actually kicked in. So if I look at the provisioned throughput. Yeah, we didn't actually auto scale above the 400 units. It's just stayed on 400 units even when I was doing that big upload. I do have one on my YouTube channel that basically shows the actual scaling of Cosmos DB, and you can actually see the actual amount of request units increasing as we do place more load on the database there. I don't know if we can view the actual requests or something. Gremlin request charges, yeah, that's showing us, and I can probably change that to the last hour or something. Yeah, and that's showing me that I was running at, 22,000 of those actual RUs. I think that's not within a second. I don't know what the actual granularity of that, but it gives you an idea of kind of how much load you're placing on the actual database and how much you're getting for the actual capacity that you are running. So I definitely recommend exploring Cosmos DB. I feel that I'm really only just scratching the surface of one of these actual data models when I'm giving this presentation. If you're working with Cosmos DB, I would highly recommend checking out the document model first. That's going to be the most useful one. It's probably going to be the most usable one in your real world projects. And instead of storing the actual graph database, you're going to be storing JSON documents and doing queries on those JSON documents. Cosmos DB at first does appear to be quite expensive. However, if you are a developer and you want to get started with Cosmos DB, if I go to this resource group, if I can actually get back to the overview section, this is in this particular resource group. So if I spin up a new Cosmos DB, and we've got this one here, I can click on Create. I'm going to go for the SQL, which is the document model, the core API, and I'll drop this into. I don't know if I can create. Yeah, I can create that in Sweden Central if I want to do that. And you've got this free tier discount. Cosmos DB, it's always been quite expensive to use compared with something like Azure Storage, and this is because it provides us with all of this, a capacity and service level agreements. So it really is an enterprise class service. However, with the free discount, you can basically get a database that you can deploy with 1,000 RUs and 25 gig of capacity, and you can have one of these in your Azure subscription, which normally would cost $64 a month, which if you're in Sweden, that'd be about 500 kroner a month that you've got for free as an actual capacity within an Azure subscription. So it's great to be able to install that and play around with it and learn how Cosmos DB works. Cosmos DB is going to be mostly used if you are going in, you're basically building a new system within Microsoft Azure. Although it talks about having this SQL API, the SQL API is really just saying that it uses the SQL query language, and this is running against the document database. So it's not really practical to take a big old existing relational database that you've got within SQL Server and migrate that into Cosmos DB. But if you're building a new application in Microsoft Azure and you're checking all of these buzzwords, like you're working with microservices, you've got an event-driven serverless architecture that you're developing, Cosmos DB is going to be a strong contender for being the best, most suitable database model to use for that new system. Okay, I think I'm pretty much out of time, but feel free to check out my other YouTube video. I'll see if I can bring that up in a browser window, and because I can probably navigate it to it here. And then in the, I think I've got an Azure section down here. Yeah, I've got the Graph of Thrones if you do want to just have a quick 15 minutes through that particular demo. And then I've got the one on doing the auto scaling and looking at how we can auto scale in Cosmos DB. And that one, I think I was showing the actual graphs of how the auto scaling kicks in. Where was that? Yeah, so you can see here the actual capacity of the database is changing as I'm placing more load on that database when I'm basically running through the demo. Okay, so thanks for tuning in and thanks for listening. I feel like I've been here almost every week and sometimes twice a week. I'm going to be taking a break now for a few weeks, and I don't think I'll be down for doing any other sessions, but there are plenty of other sessions in the series that you can check out, looking at other aspects of working with serverless technologies. There is also a track on AI and machine learning, and there's another track on DevOps, and they're all worth watching. There's good sessions on all of those tracks.
Thanks so much, Alan, for today's session. Maybe we can leave just the remaining minute to see if there's any question in the audience. But other than that, yeah, thanks so much for today's session. Great content as always. Let's have a quick look at the chat here. It doesn't look like there's any questions. Seems like everything was pretty clear.
Yeah.
So yeah, if that's it for you, I think we can leave it as that.
Yeah.
Great. Well, thanks again and have a great day.
Yeah, thanks very much for hosting me.
Thanks everybody for joining. Bye-bye.